All right. So I think we have two more presentations to go before the break. The next one will be by Atílio Gameiro from University of Aveiro. And the title of the presentation is 6G Musical, an integrated approach to joint communication and sensing for 6G networks. Uh, Atílio, the floor is yours. Please share the screen if possible, and you can go. We can see your screen now. Please go ahead. Thank you.
Okay. Can you hear me well?
Yes, yes, perfect.
Okay. Thank you, Sheriff. Okay, and good afternoon, everyone. My name is Atílio Gameiro. I'm here in the quality of the coordinator of this 6G-MUSICAL project, and I'm also a professor at University of Aveiro. And these slides intend to present an overview of the objectives, motivation, and some decisions that we have already taken in 6G-MUSICAL. And okay, so were produced with the inputs of the different partners, and basically were merged by myself and by our technical manager Izzat Darwaze. Okay. So the outline of the presentation is the following. I will start by presenting some data about the project, then define what are our goals and what are the enabling technologies, spend sometimes dealing with the motivation, the mission, and the vision that you have for this project, and then the project objectives, and then go a little bit about the architecture that you are envisioning right now, namely in terms of the types of sensing that you are considering, and one of the important points in our project is the synchronization, also the synchronization architecture, and then of course the conclusions. Okay, so concerning the data, this is an SNES project from the Call2. You have started like all other Call2 projects on the 1st of January, and the project duration will be 36 months. So, and the total effort in this project will be 435 person months. So here you have this map with the different partners. We have 7 beneficiaries, that is the people that are in the European Union, but we have also two associated partners from UK, and one associated partner from Switzerland, and also one partner from Japan, which is the Waseda University. So we cover, like say that we cover several areas. You could classify it according to several criteria, but let's say you have a significant effort on multi-node synchronization, ultra-accurate positioning, of course, the integrated communication and sensing, and we have one that I think is unique to our project, is the merging of the RF and optical technologies to enable highly accurate reference sources that then will be synchronized, of course. Okay, I suppose not of this is new for the attendance here, But just to recall the goals of 6G, there are several goals, but one that is really related to, or the most that is really related to 6G-MUSICAL, and I guess also the other projects, but that I have heard about, is the localization accuracy, which is expected to be improved by at least a factor of 30, according to the sources that I have reviewed. Okay, so the enabling technologies, again, these are depicted in several publications in the literature, and it's not so nothing new for the attendants. So the one that you are going to focus or try to develop so that it will enable new services and the new applications is the integrated sensing and communication, which of course is the topic of this workshop. There are many envisioned applications, and they have already been treated by several projects, so I'm not going to spend much time on that. So what was the motivation for the 6G-MUSICAL project? So if you look at the past, you had mainly two services over the radio technologies. One, which is the radar that provides services about localization and tracking, and the users typically were very big organizations like the military, the airports, and so on. On the other hand, we have, at least starting in the early 90s, the wireless communications that led to the different, now you are in the fifth generation. And because of the success of at least the 2G, this service, the communication service, is now massified and, let's say, democratized, which has not happened, of course, with the radar technologies. So if we, it again, in our motivation, of course, what was the motivation and what motivates us all is that we envision a future that is different from the past. Sometimes we look at the future like a rare mirror, but we want to have a future that is better, and of course, is not a repetition of the past. So what the 6G demands, I would say, at least from our point of view, and I guess most of the projects that are present here, is that we should have both services over the same network. So the radio sensing should be not an add-on, but should be embedded in 6G. What does it bring? Because the cellular communications are today 5G, 4G, 5G, and 3G also. They are a globally deployed network. So and the fact that you have massive globally deployed infrastructure, if you add these radio sensing services in the same network, so we'll expect that maybe we'll get this massification. The massification will spur the innovations, and the sophisticated services that up to a few years were restricted to big organizations can be now accessible to the masses or to the commons, to use the common terminology. And basically, this represents the figure, let's say, our vision that you have an integrated radio sensing and communications, and integrate in the, let's say, in a tightly coupled. So not two different systems that use a common infrastructure. So just to have here some key aspects of what we think differentiated 6G-MUSICAL. No? One is the tight integration that we consider that you are aiming between communications and sensing. Also consider both connected and unconnected objects, and one also other important aspect is to ensure an accurate synchronization between the edge nodes. So because with only with this accurate synchronization, if you will be able to get the very high, the ultra high accuracy in positioning or the high resolution in object imaging. And for this, I think it's something that differentiates us from the other projects. We have here tasks or work package that merge the optical and the radio technologies to achieve that. Okay, here you have some technology, 5 main technology objectives. I'm not going to detail it in very much detail. So the definition of physical and logical network architecture that integrates or contribute to this definition that integrates radio sensing and communication. Also validate physical layer waveforms that may be suitable for both communications and sensing. Multistatic sensing algorithms to produce, develop, design, and produce or generate low noise and highly stable reference sources and the associated timing synchronization algorithms. Okay, and also some aspects on dynamic resource allocations. And we have, I cannot, and we have, covering that, we have, sorry for this, I guess. You have a wide objective that encompasses all the technical objective, which is to define and validate some of the business cases that we will target and evaluate the sustainability issues. So now I'm going to go a little bit more, not so much in detail, but more focused on the architecture considerations, namely about sensing. So when you consider sensing, of course, we evolve from the radar, and we can term that in terms of classification, we can start with the monostatic, which is not more than the traditional radar concept, where the transmitted signal is directed towards the target, and then the reflection from the target is detected by the same antenna or the same array of antennas. So one clear advantage of this monostatic concept is that the receiver chain is, of course, synchronous with the transmitter chain. But the main issue is that up to right now, the radio full duplex technology is not mature yet, and so if you have to have sensing coexisting with communications, then it will be very complicated, especially if it is not a single antenna, but if it is a MIMO configuration. The other type of sensing that we call here a quasi-monostatic is quite has significant similarities with the monostatic, but with a difference that even if the transmitter and receiver are at the same location, they use different set of antennas. So the advantage is the same as the monostatic. The transmitter and receiver synchronization is facilitated. And okay, if you have the proper placement of the transmit and receiver antennas, then if the eventual problems of self-interference could be easily solvable, let's say. And one significant advantage is that, again, with the proper placement of the antennas, and if you use the orthogonal waveforms, then we can improve the angular resolution by, okay, this is the MIMO radar theory, by a factor m relative, where m is the number of the two orthogonal waveforms relatively to a phase array with a single input. So this is quite important if you aim to achieve high resolution. Okay. Okay, so of course, in then you have the third category, bistatic, which is well known from the radar community also. In this case, the transmitter and receiver are placed at different locations. So in this case, the transmitted signal is reflected at the target and then received at the receiver side. So basically, we can say that it is a channel estimation problem where then analyzing the channel estimates, you are able to extract the feature of the radio environments. So this is, in terms of concept, is similar to the quasi-monostatic, but the key difference is that transmitter and receiver are at different locations. But the angular resolution improvement, we can get exactly the same. But since the transmit and receiver are at different locations, of course, we'll need, especially if you want high accuracy and if you want high resolution, we need a very accurate internode synchronization. So this is one of the most. Another thing that may be an issue when integrating with communication is that if the transmitter is a base station, the receiver the user equipment, or vice versa, the integration arises naturally. So but if only the edge nodes are involved in sensing, then you have an additional complexity in the integration with communications, because one base station will act as a receiver for the sensing, and the other as a transmitter. And so we need to have this can be reconfigurable on the fly, but we need to have, let's say, two sets of two sets of resources that will be splitted, and that can be reconfigurable on the fly, but this represents an additional complexity. Okay, so now, okay, the multistatic, of course, is not nothing more than a generalization of the bistatic, but where we consider multiple transmitters and receivers. So going from bistatic to multistatic, of course, may have advantages in terms of applications, because the objects can be illuminated through multiple angles, and then this has the potential, as long as you have the accurate, the appropriate resolution and accuracy, it has the potential to enable high resolution object imaging. Of course, it needs, again, need of accurate internode synchronization. So basically, this was one of the one of the activities that has been ongoing, not the only one, because several work packages are progressing in parallel, but okay, that you have been considering and analyzing, and the current decision is that our project will focus on the quasi-monostatic and multistatic configurations.
Right. Thank you very much, Atílio, for the great presentation. I would like to remind everyone that you can ask questions to the presenters by clicking on the Q&A button.
Yeah, but sorry, I don't. Okay, I suppose I have exhausted my time, but I
Oh,
still.
no, sorry. I thought that you finished there.
Okay. So this was a summary. This was a summary for this for this specific aspect. So
okay. It's just we have around 4 minutes left for
okay.
the
So
presentation.
I will go first. So I did talk several times about synchronization, and really, at least from our point of view, the synchronization is a challenge. So for the monostatic and quasi-monostatic radar, transmitter and receiver reference sources are perfectly synchronous. But if even in this case, if you have procedures that require the fusion of more than one node, then you will need some network synchronization. And of course, if you consider bistatic or multistatic, then network synchronization is, of course, inherently nil. So the synchronization requirements will, of course, depend on the accuracy and the resolution that is aimed. But if you aim to, let's say, centimeter accuracy for positioning and the imaging, we need to have a very accurate synchronization. It's not very difficult to make some simple calculations that show that the internode jitter must, if you use some fusion of several nodes, the internode jitter must be quite very low. In this project, you have something that, of course, not of course, but I think the other projects have not do not have is that we to address this synchronization challenge, we merge optical and radio technologies. So in terms of the optical, you make usage of what is called optical frequency COM technology, which is an optical technology that is able to generate very high precise clocks. And then if you have an architecture that distributes it to the edge nodes, you can derive local radio clocks that keep the original purity. So this is a high-level description of the architecture that you have in mind in terms of this synchronization. So you have at a central location, or more than one, but not many, the generation of the very high purity references. Then you have an optical electrical distribution network, and at the edge nodes, we should have very high precise references, and we also consider the possibility to do some synchronization over wireless synchronization, let's say over the air synchronization. So that we can, for two reasons, for one reason that we may synchronize closed nodes faster than going back to the central point and using the protocols to synchronize them. And we consider, even if it is not a key task, we consider that This will be integrated also with GNSS for two main reasons. Okay, so I'm going to finish for two main reasons. One is that GNSS provides very long-term stability, and the other is that if you have a break in one of the links, then you will have a GNSS. Just to go. So this is an example of the distribution network that you are researching and trying to develop, but not going in details. These are some figures that the people that deal with that have reached, and have already demonstrated some of them. Now going to just to the conclusions. So I think 6G-MUSICAL is a quite ambitious project. You have identified the multiple challenge. You have already developed some results that I could not present everything here. And if I would go to the details, maybe the most appropriate presenter will be another person. But you have already defined the main architecture that will be targeting and the technologies for the synchronization. So this concludes my presentation, and I thank Sharif for his patience, and thank you thank the audience for their attendance.
Thank you very much, Atílio, and sorry for disrupting your flow there in the presentation. It's an honest mistake.
No. It was my fault because I should not put summary there.
No worries. Thank you very much. And for the interest of time, I think we go directly into the next presentation. But if anyone has any questions, please message Atílio directly, and I think he will be more than happy to answer your questions. Thank you very much, Atílio.
Thank you, Shai.